Hello everyone, my name is Selun Chen from National Taiwan University. My topic today is Enhanced Mutable Air Pollutant Abatement Performance by the High Gravity Technology, Theoretical Approach toward Practical Application. This is today's outline. First, we want to mention the energy related to air pollution emission. The energy production and use can create the most important man-made source of air pollutant emissions. They are 85% of particulate matter, sulfur oxide, and nitrogen oxide. We can see the report presented from IEA in 2016. The power generation and industry is the main resource to emit the sulfur oxide and nitrogen oxide. And also, the building can emit large amount of PM2.5. And also, the transportation is another emission source. So we want to develop the high energy efficiency technology to control the air pollutant emissions. The high gravity rotating packing bag is designed based on the two-fin theory. It can produce tiny droplets in a vase of filler, which cause more contact area between gas and liquid, and provide a high mass transfer efficiency. We can see the left-hand side figure. When the liquid goes into the reactor and from the nozzle to the packing material, when the packing bag is rotating, the liquid will be split out to the tiny droplet. In the meantime, the gas will go inside from the sideway. Then the gas will be contact with the tiny droplet to conduct the absorption. When the bed is rotating, the liquid film can be shrinkage and can break down the gas-liquid interface to narrow down the interface, then increase the mass transfer efficiency. There are many benefits of this reactor. First is generating a high acceleration by centrifugal force to form a tiny liquid film at the micro or narrow droplet. And also I mentioned it can create higher mass transfer and low liquid hold-up, high micro-mixing efficiency, high hydraulic and flooding capacity, and finally, the reactor size is very small compared to the conventional scrubber, and it's better to self-cleaning of the rotor. From the literatures, there are many different designs of the flow design of AIChE reactors. We summarize this technology for different kind of air pollutant. They are critical air pollutant, hazardous air pollutant, and the carbon dioxide. The main mechanism are oxidation and absorption. Then we can use different kind of solvent to conduct the air pollutant control in this by using the AIChE technology. This figure shows the process flow diagram of our research. This is on-site operation for air pollutant control using the AIChE system. We use the fly ash or the slag, so-called the high alkaline solid waste, to mix in the water, and we separate the liquid and the solid. The liquid, which own the high alkalinity and the high amount of calcium ion, we use this liquid as our absorbent to treat the acid gases from the flue gas through the AIChE system. The results show the effect of liquid-solid ratio for removal efficiency. We can see this figure. Higher LSR means less alkalinity input, so the pH value will be lower, and a higher LSR may not provide enough alkalinity and the calcium ion to absorb the CO2. On the other hand, ozone over nitrogen oxide molar ratio is fluctuate trend because in our research the unstable inlet NO concentration, and the removal efficiency of NO was observed slightly decreased, as in raising the LSR. The removal ratio of SO2 is remain 99% at different LSR. Second is about the effects of GLR for removal ratio. When we change the gas liquid ratio, it means increase the gas flow rate. We can see the removal efficiency of CO2 and the NOx will decrease, drop dramatically, while the SO2, the removal ratio of SO2 is remain higher. The key factor of NO absorption are alkalinity of solvent and the ozone injection dose, while the alkalinity also affects the CO2 absorption. Third one, effects of rotating speed for the removal ratio. The highest removal ratio of NO and CO2 are 96%, 92% at the rotating speed of 700 rpm. It's about a high gravity factor of 380. Even the ozone over NO mole ratio shows the fluctual trend. The removal ratio was determined by the rotating speed. When we increase the high gravity effect, the removal ratio can be achieved over the 90%. While in contrast, the removal ratio of SO2 is remain up to 96 to 98%. We can say the high gravity effect cannot increase the performance of SO2 because this pollutant is easy to absorb. Then we summarize the mass transfer characteristics, such as the mass transfer coefficient and the high transfer unit of different kind of gas. We control the three groups, such as the high gravity factor, GLR number, and the LSR number. And we can find the LSR and the high gravity factor group. When the number was increased, the mass transfer coefficient of CO2 and the NOx will be increased because it's affected by the alkalinity and the high gravity effect. On the other hand, the SO2 only can be increased when we increase the GLR number because the SO2 capture capacity is very larger in our system. Then we also create a correlation for the mass transfer coefficient of different kind of gas in our system. So the Grashof number represents the rotating speed can control the gas side mass transfer. So we determine the different kind of range of different dimensionless group. Then the Reynolds number has a positive effect on those three equations. It shows the gas flow rate can control the mass transfer process. The flow number is a negative figures, so it's no effect on the mass transfer. And the arrow bar will show the plus and minus 10% between the calculate and the experimental mass transfer coefficient. And we also compare the energy consumption, the mass transfer coefficient. From this figure of the left-hand side, the high gravity factor is around 235. Compare the different energy consumption of different gas. Then we go to on the top, we can find the favorable mass transfer coefficient. Then we go to the right, we can find the favorable enhancement factor. The final enhancement factor of NOx, SO2, and CO2 are 1.8, 6.9, and 1.6. It indicates that the SO2 was controlled by a chemical reaction. not the high gravity effect. Third part is about the particulate matter removed by AIChE process. The mechanism is about the inertial impaction, interception, and Brownian diffusion. It's similar to the wet Venturi scrub. And this is our ex experimental setup for the Coker flow type RPV for PM removal. The emission source is a diesel power generation. And the results show the particle size distribution. On the left-hand side figure, we can see the particle size of aerodynamic diameter of the particle is around the 6.5 over the uh, over the 50% are those particle size. And the property log plots show to analyze the particle size distribution of the particulate matter. Then we want to investigate the effect of a high gravity factor and the liquid gas ratio. At this figure, when the higher rotating packing bed, it means the more turbulent intensity of the gas and the liquid stream in the RPV reactor, which can beneficial to capture the fine particles. And the left-hand side figure shows the higher liquid to gas ratio can cause a related higher liquid hole bar in the packing zone. It means when we put more liquid into the reactor, they can create more tiny droplet, which can capture more particle from the gas phase. So it also can increase the collision probability of the fine particle with the liquid droplet. We also investigate the PM reduction and the energy consumption. In the left-hand side sugar, we can observe that when we increase the high gravity factor, the removal ratio will increase. But we can also balance the energy consumption because more the particle we can capture, we can save the system energy use. So on the left-hand side, a figure is a similar trend. When we increase the LG ratio, it means we put more liquid inside to a reactor from 0.05 to 0.2, 0.3. We can balance the energy consumption. So in the future, for the RPV reactor design, we have to consider the system energy consumption to our pollution control. So the conclusion will be, first we determine the mass transfer rate for the NOx, XO2, and the CO2 absorption using the alkaline solid waste as our solvent. And we can say this is a kind of green process intensification because we use the waste as a solvent, and we also conduct the pollution control in the very high efficiency. And we also analyze the energy consumption against the mass transfer coefficient under the different operating variable, so we can find the favorable operating factors. For the fine particle removal using the RPV reactor, we also found the very high removal efficiency, and we also observe the balance between the energy consumption and the particle collection. So the recommendation is also called the priority research direction is first is we want to develop a continuous operation, and also we want to treat the different kind of VOC is the hazardous air pollutant, and we want to demonstrate the scale up of our system. And we want to integrate the oxidation and the absorption in the one reactor using the mass transfer correlation in aspect simulation. And finally, we want to combine such as different tools, such as technical economic analysis or life cycle assessment, and also the CFD simulation. Based on this useful tool, we can understand the reactor design more, and we can develop more high efficiency, uh, high gravity reactor. This is my presentation today. There's a reference for you. Thank you.